Next, I will explain quantization in detail. Amplitude, as mentioned earlier, refers to the energy of sound. But how do I enter this amplitude value into the computer? Analog values, which are continuous values in an infinite number range, cannot be entered into a computer. It can only be entered into a computer if it is expressed as a limited number of numbers. The important thing here is the word limited. How can we represent values between -1 and 1 with a limited number of numbers? In other words, how many pieces should we split it into? This splitting process is called quantization. The smallest unit of data handled by a computer is a bit. A bit can express 0 and 1. By combining these 0 and 1, we handle various types of values. For example, 256 values can be expressed with 8 bits, and we call the unit made up of these 8 bits a byte. 1 byte can express 256 values, and if you express negative numbers, you can express values from -128 to 127, including 0. If you map or normalize this back to a value between -1 and 1, the value between -1 and 1 can be expressed as a specific number as shown below. In other words, values between -1 and 1 can only be expressed with the 256 numbers if we are using 8 bits. Using this concept, we can express one amplitude value within a certain range of numbers. Computers prefer powers of 2, so we usually use bits equal to the power of 2 when doing quantization. For example, if you use an integer that uses 16 bits, a total of 65,536 numbers, the values can be used between -32,768 and 32,767. If you normalize it again, it can be expressed as a value between -1 and 1. As the number of numbers representing values between -1 and 1 increases, the amplitude can be expressed in more detail or more accurately, so it is natural that the distortion of sound quality becomes less. Float 32 is a real number, representation of data that can be quantized with greater granularity and a wider range of numbers than int. You can simply think of it as the quantization method that is closest to the original sound. When quantization causes differences from the original signal, we call it quantization error. If you look at the picture, you can see that the orange line, which is a quantized original signal with int 16, manages to maintain the original signal. But as fewer bits are used, the original signal cannot be expressed properly. Let's listen to the 4 sound sources below. As the number of bits used decreases, you can hear distortion in the sound. Even if you just look at the waveform, you can see that the sound is blurred. In order to properly recover the original signal, a large data type must be used, but this has the disadvantage of increasing memory usage. You can think of it as similar to expressing such a high-resolution image with a small number of pixels, resulting in a blurred image like this.